Last time we saw that BPP is computable by polynomial sized circuits. Okay. In other words, it is in P by poly. So, we will look at another important result concerning BPP. So, what we will show today is that BPP is also contained in sigma 2 intersection with pi 2. Okay. So, remember that when we first introduced BPP, we discussed that why we do not know whether BPP is contained in NP or not, okay, because of this two-sided error thing, right. So, that is, I mean, that is still an open problem, whether BPP is in NP or whether BPP is in co-NP or not. But this is actually known. So, and this was due to the following people. So, Sipser, I think in the late 70s he proved that BPP is in the polynomial hierarchy, and then this result was due to Gax and Lotteman in 83. Okay. So, Gax actually gave the first proof that BPP is in sigma 2 intersect pi 2, but Lotteman subsequently gave a simpler proof. In fact, the proof that we will discuss now is due to Lotteman. So, I mean, so since BPP is closed under complement, it is enough to show that this is in just sigma 2, right, because BPP is equal to co-BPP. So, the idea is as follows. So, the idea is to basically and let us also assume that the random string that this machine uses has length some m. Okay, so, suppose we are looking at, so for x in 0 1 to the power n, r belongs to 0 1 to the power n. Okay. So, since the machine that we are considering is a polynomial time machine, m cannot be more than polynomially larger as a function of n. So, the idea is as follows. So, let us look at the space of all random strings. Okay. So, this is the set of all strings of length m. How many good strings do we have in this set? Suppose we have a instance which is in the language. For that instance, how many strings are there which makes the machine give a correct answer? So is the question clear? So basically, I mean, R can be any of these 2 to the power m strings. So suppose if you pick a string in the language, then what fraction of these 2 to the power m strings will make m accept x correctly?
1 minus 1.
At least 1 minus 1 over 2 to the power n, right? So basically, it's quite a large fraction. Okay, so this fraction, so this has size at least 1 minus 1 over 2 to the power n times 2 to the power n. Correct. On the other hand, so this is for correct, or let me say that for x in L, this is the set of random strings which will make it give a correct answer, or it will make it accept. On the other hand, suppose if you have an instance which is not in the language, then how many strings will make m accept?
Same. 1 minus 1.
So yeah, so no. How many strings will make m accept?
Less than 1.
Less than 1.
Yeah, so it is less than 1 over, it's some small fraction which is smaller than 2 to the power m minus n, right? For x not in L. Okay. So the idea is to basically distinguish between these two cases. Okay. So suppose I can construct a sigma 2 machine which can distinguish between these two cases, then I am done. So I'll just give some names to these sets. So given an x, let Sx be the set of all random strings such that m accepts x with the help of that random string. So what I want to distinguish is s of x greater than this number or smaller than 2 to the power m minus n. Right. Okay, so how do we go about this? So before I proceed with the proof, let's take a detour and look at some definitions. So okay, so given two strings, let's say u comma v in some universe 0 1 to the power n, let u plus v denote the bitwise XOR of u and v. Okay, so suppose you have two m-bit strings, you can consider their bitwise XOR. So that is, if both the bits are 0 or 1, you make it 0, otherwise it is 1. And similarly, given a set and some u in 0 1 to the power n, I can extend this definition to the set plus u as it has the natural definition. It is the set of all
W XOR U.
yeah, w such that w is u XOR v for v belonging to S. Yeah, so maybe I should have written this.
U belongs to S.
Hmm?
W belongs to S.
Yeah, I mean it doesn't matter because this thing is commutative, but just to be consistent, I should write this as V XOR U. Okay, I mean this operation is commutative because it doesn't matter whether you look at U XOR V or V XOR U, it's the same thing. So the first claim, okay, and let's fix a constant. So it also defines this constant K to be ceiling of m by n plus 1. So we'll come to this later on why we have this particular definition, but let's just define it this way for the time being. So the first claim is that if S of x is smaller than 2 to the power m minus n, then for all vectors u1 up to uk belonging to 0, 1 to the power m, if I look at the union of all these sets, S of x XORed with ui, for I going from 1 to k, so this is not equal to the entire universe. Okay. So in other words, what this claim is saying is that, so this is my S of x, right? So suppose S of x is small, then no matter, and if I take k vectors, no matter what k vectors I take, and I consider the XOR of this set with each of those k vectors, and I take a union of all those elements, that will never match up with the entire universe. Okay, so there will be some element here which will not belong to that union. Okay, and the reason for that is that because this set is small. Okay. Okay. So this proof is actually quite easy. I mean, it just follows from simple counting, because what is the cardinality of S of x XORed with any ui?
Less than or
S
equal
x
to
less than
or equal to S. Equal to
Can it be strictly less than S of x? It's actually equal.
equal to
It cannot be actually less than S of x also, because if you look at the XOR of ui with any element here, or in fact with any other vector, okay, for any two different vectors, it will always give two different values. Or in other words, for the same vector, it will not give. Yeah, for two different vectors, it will give two different values. By the very definition. So this cardinality is equal to S of x. Okay. So what this implies is union of cardinality of union of S of x with ui is less than or equal to. Of course, in this union you can have common elements, right? This is less than or equal to k times S of x, and S of x is smaller than 2 to the power m minus n, so this is strictly smaller than 2 to the power n for large enough n. Okay. Yeah, because k is just n by n, so it cannot cancel off 2 to the power n. So which implies that union of s of x with u of I is not equal to 0, 1 to the power n. Any questions? So
Can you saturate the original PTM to 1 minus 1 by 2 per m?
can you?
Saturate the original PTM to 1 minus 1 by 2 to our m.
What is m?
I mean, just split the plus minus.
Yeah, you can do that.
Then there will be this 2 power n minus n will be 1.
Right, so then s of x is a small set, which is fine.
That will be easier to.
Huh?
That should be easier to.
Yeah, but then we are not done. I mean, we have to look at the other side also. So the claim 2 is that if you have such an s of x, okay, and if you look at the XOR with these ui's, okay, for a large enough s of x, it would basically fill up this entire space. Okay. So if you take the error to be too small, then you might have a problem. It shouldn't matter actually. I mean, you can have m is equal to n, because you can have a randomized machine where the number of random choices is equal to the length of the input. So that can happen. Yeah. So the second claim is what I just said, that if s of x is bigger than 1 minus 1 over 2 to the power n times 2 to the power n, then there exist vectors u1 through uk such that union of s of x with ui is equal to 0, 1 to the power n. Okay. This is slightly more complicated than the other one, but these two claims together will show the actual result. So how do we prove this? So the proof is again probabilistic. Okay. So we'll prove that the probability that suppose we randomly pick these vectors u1 through uk. Okay. Suppose these are picked randomly, then the probability that the union of all these sets will not span the entire universe is non-zero. In other words, there exist some vectors u1 through uk for which it will span the entire universe. Okay, so let me just write that down. So we pick u1 through uk, which are m bit vectors uniformly at random. Okay, and then what we claim is, so we will show that the probability over all these vectors right? So the probability that they do not span the entire space is not 1. In other words, there exists a set of vectors for which it does span. Okay, any questions so far? So let us define this event. So given a string S is 0, 1 to the power n, we define the event B of S as equal to the event that S does not belong to this union. Okay. So all we have to do is we have to calculate what is the probability of the union of all these events taken over all strings S. We will define Bs of I as the event that S does not belong to S of X or Ui. Okay. So then basically this implies that Bs is the intersection of all these events. Right. So the probability that it does not belong to the union is the probability that it does not belong to each and every set Sx plus U of I. Okay. So how do we compute this probability?
These are independent events.
Hmm?
So BSI, each BSI is an independent event. Because we are
Right. So each BSI is an independent event. So once we can compute this, we'll get this. But how do we compute this?
So the size of Sx Zol Ui is same as Sx, which is greater than or equal to this. So the probability is less than 1 by 2 to the power n, 2m by 2.
Exactly.
1.
So the point is that, so what we want to check is that, so S is S does not belong to, or let's check it this way. So S is not equal to some U or U of I is the same as writing this as
U not equal to
U is not equal to S or U of I. Okay, because of the way we have defined this operation. Okay. So now we have fixed an X, and Ui is chosen uniformly at random from this entire universe. So the probability that a vector U is not equal to S or U of I, so the probability that vector U is not equal to S or U of I is the probability that U does not belong to this set. Okay, and that we know is smaller than so U does not belong to this set. So this is smaller than 2 to the power m minus n. Right. So the probability that Bs of I happens is
divided by 2 to the power n to the power minus. So 2 to the power minus n. Probability will be 2 to the power minus n because it is size of set.
u not equal to x
right. So 1 over 2 to the power n, right. No.
2 power minus n.
I'm getting confused now. So u is a vector in 0, 1 to the power n. So that is not equal to vector of the form s or u of I.
2 power minus n. Because it will be 2 power m minus n will be divided by 2 power m. Side of this 0 1 power m. So it will be 2 power minus n.
Yeah, it is not equal to. Hmm?
N is strict.
Yes, the other one is less than or equal to. I'm just thinking
This
that.
probability should be very high actually.
Hmm?
This probability should be high because it should be
No, this probability.
should be low.
because when we compute the XOR, the chance that both the strings are equal is only 1 in 2 into
No. But
Because it is equal to probability u belongs to S.
so this is for a fixed s and randomly chosen u of I. Probability is over the choice of u of I. So you have a fixed x and a fixed u. Huh?
I think you're wearing U.
No, but when I'm talking of one particular event,
You're wearing U, I think. Not all of the U's are not equal to S or U.
This is for particular u.
S and U are fixed, right?
s and u are fixed, yeah.
S and U are fixed, you are wearing over U.
So maybe actually this is not the way. Yeah, so I was getting confused because so this is actually yeah, so this actually doesn't make sense here because so what is S? If I'm picking S from the set S of X, then what we have written here is correct. Okay, but for any string S, so the probability that this is not equal to this is just depends how we are picking these two. So if these two are picked randomly, then it will just be 1 over 2 to the power m or something like that. Basically the size of the set. But actually what I want to claim here is that, let me just get this right. So the probability that S XOR U of I does not belong to S of X. So this is 1 over 2 to the power n, because all these elements, so they are uniformly distributed in this entire universe. Okay. So therefore, the probability that any one element does not belong to this set is smaller than 1 over 2 to the power n. Therefore, the probability that B S of I is true is S does not belong to S of x, so it is less than 1 over 2 to the power n. Okay, so now we have a upper bound on this probability. So now we can again bound the probability of B of S. So what is the probability of this? So this is the probability of B S of I whole raised to k, right? Because all these events are independent events. The probability that S does not belong to a certain S of x union XORed with U of I is independent with the event that S does not belong to S of x XORed with some other uj. So therefore this is less than 2 to the power minus of n whole raised to k. And what is the definition of k that we had? It was m by n. So therefore this is less than 2 to the power minus m. Strictly less than 2 to the power minus m. Okay, so yeah, so now we can write this as the probability that for some S, the event B of S happens is less than or equal to the union of all these events, the union over all S probability of B of S, and by the union bound we have this as, no, actually this is equal, but this is less than or equal to, so how many S's can we have? 2 to the power m, so this is less than 2 to the power m times 2 to the power minus m, strictly less than, and this is less than 1. So are we done yet? Yeah. So yeah, so the probability that for some S, S does not belong to this union, we have shown that to be less than 1, and that is what we actually wanted here. That the probability that there is some S in this set which does not belong to the union. So therefore there exists some set of vectors u1 to uk such that the union of S of x and u of I is the entire universe. Okay. Yeah, so the crucial thing here is that, yeah, I got myself a little bit confused here, but the property that this thing is commutative, this operation, the way it is defined. Okay, so we can write that S does not belong to U XOR U of I, or S not equal to U XOR U of I. So this is equivalent to saying that U is not equal to S XOR U of I. Okay, so now let's complete the proof. So what do we know? That X is in L if and only if this set has a large size. So when does this set have a large size? there exists vectors u1 through uk such that for all strings r, or let me just put it as s, since I am using s here, for all strings s, S belongs to the union of S of x XOR u of I. Okay, so this is what we have, and now the thing is that we have to convert this into a sigma 2p definition. So this can equivalently be written as there exist vectors u1 through uk such that for all s, if I look at this machine M that is given the string x and another string which is basically the random string that it simulates, s XOR u of I, this machine should accept. Okay, and we just don't make one run of this machine, we make several runs of this machine, and if just in one of those runs the machine accepts, then we accept. Okay, because let's just pause here and see what this statement is claiming. So this is claiming that for all strings x, all strings s in the universe, if this machine is provided with s and some u of I, okay, then it should accept x. And that is what we know from our initial definition, that if x belongs to the language, then there is some u of I for which all strings s will belong to this union.
Earlier I was saying that can we saturate even PTM to 1 minus 1 by 2 to the power m. I don't think that is possible, because when we saturate the PTM, then this random string also increases the size of random string.
The length of the random string.
Because we are consecutively limiting 2, 3 PTM. That will increase the length of random string.
Yeah, that is true.
We cannot saturate to 1 minus 1 by 2 to the power m.
That is true. Okay, so yeah, so let's look at a couple of more things. So, so similar to BPP, we can also define the log space analogs of these classes BPP and RPP. So log space probabilistic classes. Okay. So we have the class BPL. Okay, so I won't go ahead and formally define it, but this is just a log space analog of BPP. So there is a probabilistic machine which uses log n amount of space, and it makes an error of at most 2 by turn. And we also have the class RL, which is the log space analog of RT. So there is one very interesting problem which is contained in this class RL, and that is the problem of undirected reachability in graphs. So recall the path problem that we defined. Okay. So similarly, we can define the problem U path. Okay. So this is given a graph G and 2 vertices S and T, okay, where G is an undirected graph and there exists a path from S to T. Okay.
Is this the intermediate step in proving that U path is in L?
So what are you saying? Which is
U path
intermediate?
belongs to L.
Right.
So is this problem is intermediate step in proving?
Yeah, sort of. Because this was the first non-trivial result that was shown about the undirected path problem. Okay. But then there were subsequently many improvements over it, and only in 2005 it was shown that this is in L. So I'll just quickly mention some of those things, but it is very important to understand this RL algorithm. So this was shown in 79, I think 79 or 78, that U path is in RL. Okay. And this algorithm is quite simple. So what this algorithm says is that yes. It is in NL, of course, because you can always guess a path and get the correct answer. But it has been shown that it is in L as well. So there is this whole sequence of results. So first it was shown in RL in 79. Then I think in late 80s it was shown that this problem is in L to the power 3 by 2. So what that means is D space log to the power 3 by 2n. Okay. Then I think in 2000 or 99, sometimes in the late 90s, it was shown that this problem is in D space log to the power 4/3 of n. And then finally, it was shown by Reingold in 2005. That this is in L. That kind of settled the complexity. This was a very important line of work because I mean, as we all know that the directed version of this problem is hard for NL. Okay, so any improvement on the directed version would immediately give a collapse on the class NL. Okay, so for the directed version, for example, we don't even know whether it is in RL or whether it is in 3 by 2. I mean, the best we know is by Savage's theorem, which is log square. Because yeah, if you can show it is in RL, that would immediately imply that NL is contained in RL, which is not known. So yeah.
The last result a de-randomization result.
Which one?
Last result.
I mean, all these are de-randomization results actually. All these results kind of look at this and do some kind of a de-randomization. But this is, I mean, more complicated. I mean, it uses this theory of expander graphs. Okay, so expander graphs are undirected graphs which have very low degree, okay, but very high connectivity. So when I say high connectivity, it means that the diameter of these graphs are very small. So from one vertex in the graph, you can go to any other vertex, let's say in log n number of steps. But these are certain things that you expect only for graphs which are very high degree, right? So expanders are graphs which simultaneously have both these properties. So what Reingold did was, he took an arbitrary undirected graph and then he converted it into an expander. Because once you have an expander, once you have a graph which has a diameter, let's say, of length log n, you can do a brute force DFS or something and you can solve it in L. Because suppose the graph has constant degree, let's say it has degree 2, okay, and it has diameter log n. Then you can always keep a log n bit vector which will help you to do a DFS. I mean, whenever you are going left, you store 1, and whenever you are going right, you store 0. and you can explore all possible paths from S to any vertex in that component. But the crucial thing about his thing is that how do you convert a general undirected graph into an expander? So that was the heart of his proof. Okay, so yeah, what I was mentioning here is that the first result in this line of work was this thing which showed that undirected path is in RL, and the algorithm is quite simple. What the algorithm does is it starts at S, okay, and it just performs a random walk of some polynomial length. I think it does a random walk of some 8 times n to the power 4, where n is the number of vertices. And it claims that if T is reachable from S, so in an undirected graph, reachability is the same as checking if two vertices belong to the same component. Right. So if S and T belong to the same component, then what they argued is that with probability greater than half, you will reach T. And of course, if T does not belong, if S and T do not belong to the same component, no matter how long you walk, you will never reach T. So the other direction is quite easy. So one direction is a little bit non-trivial, but it's also not that complicated. So what I will do is I will not prove this result in class, but I'll just post a link to a proof of this theorem. Okay, so those of you who are interested, you can just go back and read it. So it's not very difficult. It's about a 1 or 2 page proof, but it's a nice argument. Okay, so I'll.
So how does it use the undirected property of the graph?
So it uses the undirected property because it checks for the fact that two vertices are only in the same component. Because in directed graphs, there can be two vertices which are in the same component, but there might not be path between them. But here they are using that. So what they show here is that, I mean, again, let me give the idea, is that if you have a stationary distribution on your graph, okay, so a stationary distribution is, again, if I want to informally define it, it is basically assigning probabilities to every vertex of your graph, such that if you take one step from any vertex, okay, the next probability distribution that you get is the same as your original distribution. Just to give a quick example, so suppose you have a triangle. Okay, so this is the graph, and let's say you are with equal probability of 1/3 likely to be in any of the 3 vertices. Okay, and then suppose if you take a step from a vertex, so let's say this is A, B, and C. So suppose if you go from vertex A to B, okay, so let's say the probability of going from A to B is half, and the probability of going from A to C is also half. So what is the probability that you were at A and in the next step you go to B? 1/6. The other way also that you can come to B is from C. What is the probability that you were at C in your previous step and you come to B? That is also 1/6. The probability that after 1/6 you are at a vertex B is again 1/3. So in this graph, no matter how long a walk you take, if you start with this distribution, you will always remain at the same distribution. So this property is not true for directed graphs. In directed graphs, this notion of stationary distribution is not guaranteed. In an undirected graph, you can show that any undirected graph, there is always a stationary distribution for that graph. But so that is a crucial difference. But anyway, I mean, I don't want to go into the details of that. I just post that link and you can have a look.